Hey, this is Mr. Ayton. This is Pre-AP Chemistry, a new unit, Unit 14 Kinetics. This is week 31, and we're going to learn a whole bunch of stuff in this Kinetics unit. We're going to be taking a look at reaction rates. We're going to be taking a look at the rate law. How do you calculate a rate law from experimental data, especially from concentration versus rate? How do you find the rate law from graphical data, concentration versus time? How do you find the half-life from graphical data? And what are some factors that increase the rate of a reaction? So this is Unit 14 Kinetics, week 31. So what is a reaction rate? You don't even know what a reaction rate is, but we're going to be taking a look at what a reaction rate actually is. And a reaction rate is how fast the reaction is occurring. Okay, it's the amount of molar per second. It is a rate of how fast a reaction is occurring, which means the reactants are disappearing at a certain rate and the products are appearing at a certain rate. And if you can see here, the N2O5 gas is disappearing at a rate of 4.2 times 10 to the negative second molar for every second. So every second we're using 4.2 times 10 to the negative second moles per liter of this substance. Well, how are we going to figure out the rate of appearance? We're just going to go to our molar ratio. For every 2, we're going to produce 4, and we're going to produce 1, which means for every 4.2, we're going to produce 8.4 times 10 to the negative second molar per second. That's the rate of appearance of the nitrogen dioxide. For every 2, we're only going to make 1, which means for every 4.2, you got it, 2.1 times 10 to the negative second molar per second. That is the rate of appearance of the oxygen gas. So the rates of disappearance and the rates of appearance goes by, because we're talking about moles here, it goes by a molar ratio, because this is moles per liter per second. It is how fast the reaction is occurring. Well, we have this thing called the rate law. And what a rate law is it's how much that reactant matters in order to make the reaction go faster, okay? And there are 3 different orders of reactions. There's what's called a zero-order reaction. Now, anything to the 0 power is 1, which means if you double the amount of A, it doesn't do anything. 2 to the 0 power is 1. 1 to the 0 power is 1. If you multiply this reactant by, if you increase the concentration by a whole lot, the reaction's not going to get any faster. The rate is going to stay the same. Now this one here, first order, this is a directly proportional relationship, which means if you double the amount of A, double the concentration of A, put twice as many moles of A in, the rate is going to get double. The rate is going to get double. If you triple the amount of A, it's going to triple the rate. It's going to make your reaction rate go faster because you have more particles that are colliding and reacting together. And last but not least, we have what's called second order. Second order is a squared relationship, or a quadratic, a squared relationship, which means if you double the amount of A, the rate is going to multiply by 4 times. Okay, if you triple the amount of A, the rate's going to go up by 9 times. It is going to be a squared relationship for this, okay? And so we can know this, we can figure out the rate law by the experimental data, okay? So first let's take a look at, we're just going to zero in on the nitrogen monoxide, the NO. How are we going to figure out the nitrogen monoxide? Well, we want to take 2 experiments where the hydrogen gas is not doing anything. Okay, and if you can see, this is only the reactants, because the reactants indicate how fast your reaction is going to occur, okay? And so we're going to take a look at experiment 1 and 2. Why are we going to take a look at 1 and 2? Do you see how the hydrogen gas does not change, which means it's not coming into play. We're really just looking at the NO. And so look at the NO. It goes from 0.0050 to 0.010, which means this concentration doubled. Well, look at what happened to the rate. The rate went from 125 up to 500. So if you don't see that, divide the bigger one by the smaller one. If you take 500 divided by 125, we get it multiplies by 4. Now just think about that. We doubled the concentration of NO and the rate quadrupled. Which one is that? Is that 0 order, first order, or second order? That's second order. So it's second order with respect to the NO gas. Okay, it's second order with respect to the NO gas. Now we gotta next find out what's going to happen with the hydrogen gas. Okay, so we're going to zero in on the hydrogen gas. Which two experiments are we going to look at for the hydrogen gas? Well, let's look at 2 and 3. Why are we going to look at 2 and 3? Do you see why the NO stayed the same? It's not coming into play here. And look at what happens to the concentration of H2. It went from 2 to 4. It doubled, didn't it? It doubled. And look at what happened to the rate. The rate went from 5 to 10, 0.000. It went from 5 to 10, so it doubled. So the concentration doubled, the rate doubled. Which one is that? Is that zero, first, or second order? That's first order. So it's first order with respect to the H2 gas, isn't it? First order with respect to the hydrogen gas. So now that I know my orders of both the reactions, that gives me what's called the rate law. Your rate is equal to K is a constant, times NO to the second power, because it's second order, times H2 to the first order. So you can see that is called the rate law. And so that is the rate law. You can see if you double the NO, it's going to multiply the rate by 4 times. If you double the H2, it multiplies the rate by 2 times. And we have this K, this constant. I hope you can see this isn't like a Y equals MX format, okay? So it's second order with respect to the NO, first order with respect to the H2. Overall, we call that third order. And you can put a 1 up here if you want. You don't have to. Remember, if it's zero order, you don't even have to put it in there, because anything to the 0 power is 1. Okay, and so that's called the rate law. And that is from when we're given concentrations and the initial rates. Okay, well, there's another way to find the rate law, and that is by the graph. If it's zero order, the graph of concentration versus time, so the concentration of a substance versus time, would be linear. If it's zero order. If it's first order, the natural log of the concentration versus time is going to be linear. If it was second order, you would do 1 over the concentration versus time, and that would be linear. So the linear graph is going to tell you if it's zero, first, or second order. Well, just take a look. We have 3 graphs here. It's all the same data, but it's just looking at the data differently. This first graph is concentration versus time. This second graph is natural log of concentration versus time. This graph is 1 over the concentration versus time. Which graph is linear? Only this second graph right here, which is natural log of the concentration versus time. Which means what order is this substance going to be? It's going to be first order. Which means if it's first order with respect to the N2O5, the rate law would be rate is equal to K times N2O5 to the first power. And so you would know it's first order. If this wasn't a linear graph, but this was a linear graph, you would know it's second order. If the first graph was a linear graph. So the graph that's linear is going to tell you, is it zero, first, or second order? Okay? And next we're going to take a look at the half-life determination from graphical data. Now this only works for the half-life only works for first order. The half-life will be consistent for first order rate laws, the first order rate laws. And you can see the half-life is the time it takes for the concentration to be cut in half. So here my concentration is at 0.20, and do you see how to get to 0.10, it took exactly 7 seconds. It took exactly 7 seconds, which means that's the half-life. Then we go from 0.10 to 0.05, and how many seconds did that take? It took 7 more seconds. Then 0.05 to 0.25, another 7 seconds. So the half-life, what we call T1 half, is going to be 7 seconds. That is the half-life of this reaction. And we know this is rate is equal to K times whatever concentration is to the first power, because it is a first order rate law. The half-life is consistent. It's going to go from 100% down to 50%. And for this reaction, it takes 7 seconds. To go from 50% down to 25% takes 7 more seconds. To go from 25% to 12.5%, it takes 7 more seconds. So we know it would take 7 times 3 is 21 seconds to get 87.5% of it gone. It's never going to hit 0. It's going to asymptote. And of course, if we graph the natural log of the concentration of this data versus time, we would get a linear graph here, okay? Because it is first order, and that's how we find the half-life determination. Well, there are about 4 main factors that help to increase the rate of the reaction, to make the reaction go faster. The first is greater concentration. Now remember, for zero-order reactions, you pump more concentration in, nothing's going to happen. It's to the 0 power. So this only works for first and second orders, and if you have more concentration, there's more particles that increases the probability of effective collisions. Remember, rates of reaction, how fast reaction occurs, is all about collisions. There's the more increased number of surface areas. Why does increased number of surface areas or breaking up into smaller particles end up reacting faster? Well, it increases the frequency of collisions, okay? There's also the greater temperature. If you increase the temperature, it increases the average kinetic energy, and therefore the frequency of collisions begin to increase. And last but not least, it's using a catalyst. A catalyst lowers the activation energy by providing a new pathway. So using a catalyst ends up increasing the rate of the chemical reaction by lowering the activation energy. So 4 factors that increase the rate of a chemical reaction. And that is Unit 14, Kinetics, Week 31. And that is the speed of a reaction. Take care, guys. I'll see you.